Hello everybody, my name is Moufdi Hadjab from Sila University in Algeria. Today I have to present my work entitled Molecular Dynamic Simulation of Furan-flanked Diketopyrrolopyrroles for Organic Solar Cells Manufacturing with collaboration with Dr. Olga Guskova from IPF Dresden in Germany. So our presentation is synthesized according to this point. First of all, we have to start with the preface arising the question, why the molecular dynamic simulation? After that, we have to show the simulation and the result and the discussion as well, and finally conclusion and perspective. In this work, the Diketopyrrolopyrroles DPP-based small molecules are investigated theoretically using molecular dynamic simulation MD, as it is shown in figure number 1. And first, we have to calculate the geometries of DPP flanked with two Furan rings in trans-cis, trans-trans, and cis-cis conformations using FORCITE module of Material Studio 9.0. So the dynamic molecular simulation MD, one of the numerical tools in the theoretical study of small molecules, polymers, etc. This computational technique calculates the time-dependent behavior of molecular systems. This method is now usually used to investigate the structure, dynamics, and the thermodynamics of small molecules and their complexes. A simplified description of the standard molecular dynamic simulation algorithm when we start with assign velocities to all atoms and calculate forces on all atoms. After that, using the Newton's second law of motion, which describes the relationship between the M and E. Again, calculate velocity for the next time step and using the change of velocities to get coordinates for next time step. Finally, going to the step number 2 above. So the main goal of the work is to understand the relationship between the conformational state of the molecules and its behavior of the graphite surface. Let us start by comparing the structures of the monolayers after 1, 2, 3, and 4 nanosecond runs, which are depicted in figure number 2, 3, and 4. Then we construct 3 model systems comprising 100 conformers on a graphite surface. In this simulation books of 50 times 50 times 50 nanometer. After that, the MD of the adsorption monolayers is studied in MVT ensemble at room temperature. So here we analyze the molecular systems by calculating the concentration profile, the intra and intermolecular hydrogen bonds, the mean square displacement MSD, as well as the diffusion coefficient D using the Einstein equation. So the concentration profile shown in the figure 5 are calculated along the 001 direction. L, the system demonstrates the formation of a monolayer, which is proved by only one maximum on the profile. The MSD is calculated also, and the slope defines the self-diffusion coefficient D according to Einstein equation. So, the mean length of the hydrogen bond is 2.5 angstrom for cis-cis, as it is shown in this table, which is the shortest, in other words, the strongest one, which facilitates the formation of the stripes. So, in summary, the molecular dynamic simulation demonstrates that the conformational state is essential to the properties of the layers. All the conformers show a quick self-assembly. However, the length of the hydrogen bond and therefore the intermolecular coupling are dependent on the conformation. Here, the most strongly bound stripes are on the basis of cis-cis. As perspective, DPP-based conjugated materials show strong crystallinity and high-hole electron mobility, indicated that they can be used as both electron donors and electron acceptors in organic solar cell manufacturing. And finally, thank you so much for your time and attention.